Okay, thank you very much for your hospitality. And I see some students are there, so it's a very good opportunity to learn, start. So this first lecture is basically introduction to power quality. Okay, and you can see the outline of the presentation. So first we will see what is the definition of quality of electrical energy, as Professor Madhusudan was explaining, right? Justification of interest in electrical power quality, classification of power quality problems, because there are so many problems related with power quality problem, different factors concerning the harmonics and some standard related to power quality. So this is what we are going to discuss. So if you see what is power quality, so this is what is the question, as Professor Madhusudan was saying. So during the transmission, distribution and utilization of electrical energy, the voltage may vary. Why the voltage will vary? There are so many phenomena why the voltage may vary. Perhaps there is a fault in the line, or there is a very large size induction motor is starting. So as you know, during the starting in the large size induction motor, they may take 5 or 6 times of rated current may flow. So that heavy current will flow through the impedance of the line, and because of that voltage drop is there. So at point of common coupling there may be some voltage sag, or perhaps there is some capacitor bank. Okay, capacitor bank, you are switching on or off. So if you are switching off the capacitor bank, what is the purpose of capacitor bank? That it is providing the capacitive reactive capacitive current, so that the source does not have to provide the reactive current to the load. So if you are switching it off, that reactive current will be supplied by the source, and the current will increase, and perhaps it may cause the voltage drop. Or there may be a large load which is switched on or switched off. Because of that, there may be some voltage variation. So this is what the term power quality is associated with, this variation of voltage and electric energy. Sometimes customers say the power quality is the power without over voltage transients, without voltage sag, without short or long term interruptions, without flicker. So there are so many things. So the power quality is related with those things. According to some customers, power quality is concerned by a perfectly sinusoidal wave, a constant amplitude and a constant frequency, because at certain application, for example, in the hospital, if the frequency changes or voltage changes, perhaps some equipment may malfunction and the life of patients may be in danger. So that's why it is very important to have constant sinusoidal voltage and constant frequency, or maybe some electronic equipment also. According to utilities, power quality is associated with the reliability and show statistics demonstrating that the system is 99.98% reliable. This is what utilities may say. Like you have DESU, I think you have DESU here. I don't know if it is still there, or UP Electricity Board or those things. So what they will say, okay, in 24 hours, the electricity was not there for few minutes. So if electricity is not there, but here this may be different, but I am talking about North America. like if electricity is not there for few minutes, so this is right that it is very reliable, 99.98%, because in 24 hours, if few minutes of electricity is not there, you are still reliable, 99.98%. But what impact it will have on industry? So it is just an estimate. Only in North America, every year, more than $100 billion are lost. $100 billion are lost every year because of the short interruptions and those things. So though it may look very small thing, okay, for a few minutes electricity was not there, but it has very high implications. According to the load equipment manufacturers, quality power may be defined as those characteristics of the power supply that enable the equipment to work properly. Okay, but these can be very different for different equipment and different manufacturers. For example, here you have 220 volt. I remember when I was a kid, sometime voltage was 180, 190 volt. Okay, so we used to, for the TV, we used to have a knob, we used to adjust the voltage, right? So for some application like radiators to heat the room, the voltage may vary, okay, 190 volt or 230 volt or so. It is fine, they will still work and proper. But in some equipment, they may fail, they may malfunction if there is a variation of voltage. So it depends basically, different equipment, different manufacturers, what is their standard. Finally, power quality is a customer-driven issue, and the customer's point of view is the most important. Therefore, a power quality problem may be defined the following way: any power problem manifested in voltage, current or frequency deviations that results in failure or misoperation of customer equipment. So there we say there is power quality problem. Power quality equal to voltage quality, as Professor Madhusudan was saying, this is what generally say, power quality is voltage quality. So the power supply system, utilities can control the quality of voltage. It has no control over the currents that particular load might draw. Okay, so the generators may provide near perfect, because you know we are having large generator, they are providing near perfect sine wave. The distorted currents pass through the impedance of the system can cause the distortion of voltage, because if there is a fault in the line currents, and it may, that current, heavy current is passing through the impedance of the line, and it may cause voltage sag. Like lightning stroke, if there is a thunderstorm and lightning stroke may cause impulsive high voltage which may damage the equipment, like your transformer may be burned down, right? Currents for harmonic producing load. So these non-sinusoidal currents, they are flowing through the impedance of the line, which will cause the voltage drop, distorted voltage drop. And finally, at the PCC, point of common coupling, you may have distorted voltage. So what is PCC? Point of common coupling. Point of repartition of responsibility between the utility and the customer. That is PCC, point of common coupling. It is the responsibility of the utility to provide the voltage and current without any pollution. Although the current is the responsibility of the customer, right? So it is the responsibility of the customer not to distort the voltage and the current. So as you can see, some example of PCC, point of common coupling. So this is the utility system, supply system. And here is one customer, suppose under study, and this is the transformer of the customer, and there are other customers here. So basically you are saying here, this is the point of common coupling. But in this example, you can see This is the utility system and other customers, and this transformer is perhaps provided by the utility company, and so PCC is here basically. Point of common coupling where many customers are connected there. So if one customer is creating problem, so PCC, it will be reflected on the PCC, and the other customers will also get affected. There was a survey which was done few years back on the causes of power quality. So this is the perception of the client, and this is the perception of the utility company. So you can see there are some changes in perception. For example, clients say, okay, natural cause is 60%. Okay, what is the natural cause? Like, as I discussed, there is a thunderstorm and lightning stroke, and because of that, transformer burned down. Or there is a storm came, hurricane came, and the tree fell on the distribution line. So those are the natural causes. So according to the perception of the client, 60% causes, while the utility company says it is 66% cause. While the problems caused by utility, according to perception of utility company, it is only 1%. And according to the client, utility has 17% of the problem. Sometimes actually, you know why this perception is different? Because perhaps sometimes the equipment of the client is very old, and if there is some variation in voltage, and you can see, so it may malfunction, then the client may blame the utility. Okay, because of the bad quality, my equipment did not function. So this is basically a difference in perception, right? And the customer is 12%. You know what happens, that suppose there is some large capacitor bank and it is switching on and off, which may generate transients, and because of that your variable speed drive may trip. So customer will say, okay, this is caused by the capacitor bank installed by the utility, but the utility may not see this thing. So that's why difference of perception. Like from customer point of view, it is coming from the utility, while there is no monitoring equipment for that. So that's the problem. Okay. Neighbors, 8%, according to the clients and neighbor. What the neighbors can cause? Sometimes what happens, there is a one client which has the linear load with reactive power, and it has put the capacitor bank at the entry of the industry to improve the power factor. But there is another neighbor, some industry nearby, which is generating harmonics. So those harmonics are attracted by the capacitor bank of the earlier client, and those harmonics will come and they will heat up, and sometimes they may burn the capacitor bank of another client. So this is what happens, problems caused by the neighbors. Justification for interest in power quality: load equipment is more sensitive to power quality variation than equipment used in the past. Why it is more sensitive? Because now we are using more and more electronic equipment, DSPs and those, so they may be more, they are more sensitive to variation in power quality. Increase in harmonic level on power network. Why there is an increase in harmonic in power network? Because many times utility companies ask the client to improve the efficiency of their equipment. So to improve the efficiency of the equipment, they will be using power electronics, converters and those things, and then it will increase the harmonics. But sometimes utility companies they encourage customers, like I remember 15 years ago, Hydro-Quebec is the utility company in Montreal in Quebec province. At that time, LED bulbs came in the market, and Hydro-Quebec was encouraging everyone to buy those LED bulbs because they will consume less power. Okay, so why Hydro-Quebec was giving 50% off on all those bulbs? Because so that more and more customers buy those LED bulbs and they put, and why? Because it will increase the efficiency, less power consumption, then they don't have to build the new power plants. They may delay the construction of power plants. Otherwise, if they don't do anything, if they don't increase the efficiency, if they don't encourage people like this, then you will need more power plants needed, more transmission line, more right of way, so it costs money. So it is in the interest of the utility company to have the more efficient equipment at client's home so that less power is consumed. Increase awareness of power quality issues by the end users. Now everybody is aware that, okay, my equipment may malfunction if power quality is not good. So they may complain that, okay, utility company has to improve the power quality. Many things are interconnected in the network. Integrated process means that the failure of any component has much more important consequences. The cost of short and long-term interruption runs in billions of dollars, as I have already told you. More than $100 billion just for a few minutes of interruptions. Protection against, what is the industrial and commercial advantage of power quality? Protection against interruption of production. So if you have a good power quality, it is a kind of protection you are having. Otherwise, there will be lost time because for few minutes there is no electricity. It may perhaps create problem in the industry like loss of production. Okay, like for example, there is a chemical industry, they are making some medicine or some other chemical product, and on the pipeline in the machine that product is flowing and suddenly there is no electricity. What will happen? You have to, chemical industry has to keep certain temperature and pressure, otherwise the product may not have the desired chemical requirement which are supposed to have for the drugs, for example. Then company has to clean all the pipes and the equipment, the product will be thrown away. So this is the loss of production. Efforts to restart, washing out everything from the pipe so that it does not go to new product and those things. Lost sales, now you will have the delay in deliveries and those things. Okay, and sometime if the power quality have like spikes and those things, it may damage the equipment, then the maintenance cost of replacement and cost of repair, those things. So that's why it is in the interest of everyone to have a good power quality to avoid those problems. For residential customer, no financial loss, because during the daytime, if there is no electricity 1 or 2 hours, it does not matter because nobody is at home. Kids are gone to school, adults are gone to work, so it does not matter. So there is no financial loss. However, when you return home in the evening, then you will see a blinking clock. You have to adjust those clock, maybe 3, 4, 5 clocks you may have, so you have to adjust the time and everything. If the customer complains, the utility has to send a technician. But technician will come, what can he do? Okay, there was no electricity for, I remember 20 years ago, there was something happened and my VCR was burned out. Then I called Hydro-Quebec, oh, there was not good power quality, my equipment is damaged. So technician came, that's fine, the technician came, but he did nothing, nothing happened. So, but anyway, the utility company has to send someone, so it costs money, right? Bad publicity of the utility, Consumer Protection Group may ask for the inquiry of poor power quality, and in that case utility will have to hire an advocate. So that cost, so bad publicity is not good for the utility company. Categories and characteristics of power system electromagnetic disturbances. First, the impulsive transient, you can see. So in certain, you see microseconds, you have 20 kiloampere of current for few microseconds. So this is impulsive transients. Okay, positive or negative unidirectional, very rapid increase in voltage at high frequency, independent of source voltage frequency. Suppose you have 50 Hz or 60 Hz, but it has nothing to do with this. It is in microsecond high frequency. Impulsive over voltage is characterized by rise time. So you see, this is an example, impulsive voltage. So rise time is this, 1.2 microsecond. Peak value, for example, it is just an example, okay, 2000 volt in 1.2 microsecond. And drop time to 50% off. 50% means 1000 volt. So here you can say this is the drop time up to the 50% of peak value, maybe 50 microsecond or something, that depends. Impulsive over voltage is diminished rapidly depending on the increase in the distance between the perturbation source and the load. Impulsive over voltage is caused by lightning stroke, network manipulations. Oscillatory transients, this is just an example of transient caused by capacitor switching, back-to-back capacitor switching. So you can see oscillatory transients are there, high frequency oscillatory transients. Instantaneous value change rapidly independent of the source frequency. So oscillatory over voltage is characterized by spectral content, its duration, its amplitude. It is frequently encountered in distribution network, caused by mainly by the capacitor banking. It may be depending on the capacitor and inductance, it may be high frequency, 50 kilohertz or 500 kilohertz or 5 to 500 kilohertz or less than 5 kilohertz. Transient phenomena may cause the following problem: equipment damage after the lightning stroke, breakdown of distribution transformer after thunderstorm, breakdown of customer's surge arrestor, tripping of variable speed drive without voltage sag or brief interruption, damage to customers' capacitors. Short duration voltage variation. Okay, so you can see for short duration, for few cycles, you have voltage sag. In Europe, they call it dip. So voltage sag may be between 0.1 pu to 0.9 pu, between half cycle and 1 minute. So that is short duration voltage sag. So if we say 20% sag, it means VRMS is 0.8 pu. Voltage sag is caused by high current flow due to system faults, starting of large motors, as we have already discussed. Short duration voltage sag may cause the following problems: abnormal variation of voltage, tripping of variable speed drive, tripping of arc lamps, temporary diminution of light. So here you can see one example, voltage sag caused by a single line to ground fault. So you can see voltage sag, it's around 20% of voltage from around 100 volt. It came to minimum 17.44 volt. So it is around 80% voltage sag for around 3 cycles. So this is just an example of voltage sag caused by single line to ground fault. And this is the voltage sag caused by motor starting. As I was telling you that if you have large induction motor, then for few seconds, like in this case 3.2 second, you have a voltage sag here, and 20% voltage sag because the voltage has gone up to 80% here. Short duration voltage variation, temporary over voltages. See, you have over voltages for short duration. Voltage swell, we call it swell. Sudden increase in voltage between 1.1 pu to 1.8 pu between half cycle and 1 minute. So swells are caused by unsymmetrical faults on the system, shedding of large load, energization of large capacitor bank. So these are the causes of the swell. Swells cause the following problem: abnormal variation of voltage, tripping of variable speed drives, breakdown of surge arrestor, temporary increase in illumination. So this is just an example of the swell. Okay, it is caused by single line to ground fault. Suppose there are two parallel lines, and if one parallel line is tripped, then the voltage may increase on the first line because there will be less current, less drop. So because of that, voltage swell is there. So in this case, you see maximum it has gone to 15%, around 15% temporary over voltage. Although this is not very clear, but it is here. Yeah. Short interruptions for certain period of time, there is no electricity. This is the short interruption. The voltage is between 0 pu and 0.1 pu. And there are three types: instantaneous, momentary, and temporary. Instantaneous if it is between half cycle and 30 cycles. Momentary if it is 30 cycles and 3 seconds. And temporary if it be more than 3 seconds and less than 1 minute. So this is short interruptions caused by open closed cycle of circuit breaker of overhead transmission distribution line. It may cause the following problem: impact on industrial product, as we were discussing, tripping of motors, tripping of arc lamps. Under voltage, a brownout. So this is what I was telling you when we were young and I was in Bulandshahr, and many times voltage was there, but you could see the light coming out from the bulb was very less. And if you switch on the TV, then you can see the voltage is 180 volt or below that. So we used to have a regulator, voltage regulator. We used to move the switch so that the voltage, because it was a perhaps stepping transformer. So this perhaps may be the strategy used by the utility companies to reduce the consumption, electricity consumption. If there is less energy is generated, they may reduce the consumption like this. So the voltage, maybe this is under voltage 0.8 pu to 0.9 pu for more than 1 minute, caused by switching of large load on the network, switching of large capacitor bank. Over voltage, permanent, long duration voltage, permanent. If it is more than 1 minute, then we call it over this permanent long term duration voltage variation. 1.1 pu to 1.2 pu, caused by switching of large load on the network, switching on large capacitor bank, because you have switch on the large capacitor bank, so the capacitor bank is supplying the reactive capacitive current, so less current is coming from the source, so less voltage drop, so because of that there is a over voltage for certain time. Inadequate voltage regulation, incorrect choice of transformer tappings. Over voltage or under voltage are generally not the results of system faults, but the variation of load or network changes, right? Some large load is put or large load is off or capacitor are on off, so those are causing over voltage, under voltage. Voltage regulation equipment should be used to correct the problem. Sustained interruptions, if there are more than 1 minute, your voltage is 0 pu. This is called sustained interruptions caused by incident of permanent nature, like some storm came and the tree fell on the line or transformer burned out. Breakdown of power apparatus which requires repair to restore, like your transformer is burned out, now it has to be replaced or repaired. So sometime in Montreal we have hydro-quebec truck is there, so that will come with a large transformer. Temporarily they will connect that transformer to replace this. This is what happens. Voltage unbalance. Three-phase system voltages are not equal in amplitude, or they are not shifted at 120 degree relative to each other. So how you calculate the voltage unbalance in percentage? So this is the maximum of deviation between phase A voltage. See, deviation in phase A voltage, difference between the average voltage and VRMS, or phase B, DVB, or phase C. So you see which one is maximum, divided by the average voltage multiplied by 100, it will give you voltage unbalance in percentage. Usual causes of the voltage unbalance: single phase load of different customer on three-phase distribution network. Like sometime it happens in our ATS, also in my institute, that different floors, they are coming from different phases, so they may not have equal load, so that is called the single phase load on three-phase system, different loads, so it may cause voltage unbalance, or it may cause by arc furnace or electric train, etc. Blown fuses in one phase of three-phase capacitor bank. So suppose you have three-phase capacitor bank, one of the phase fuse of the capacitor bank is burned out. So A is burned out, B and C they are still providing. So the A reactive current, capacitive current is not provided by the capacitor bank. So it will have more voltage drop, because the more reactive capacitive current is drawn for phase A from the source, while B and C they are still compensated by these things. Geometrical asymmetry in overhead transmission lines. Why there will be a geometrical asymmetry in overhead? Because sometimes transmission lines, they run for thousands of kilometers, like here also, but in Canada we have, in the north we have thousands of kilometers away we have Bay James, a big hydropower plant, and from there 3,000-4,000 kilometers of transmission line is coming to Montreal area, but it is coming through the lakes, mountains and other structures. So the capacitance between the overhead transmission line and the mountain, or the capacitance between the transmission line and the lake, the capacitor may be different, so it may causes the asymmetry in distribution. So how to correct it? So this is nothing new, this is the transposition of conductors we do, like position A, phase A, After few kilometers, you change the position of phase A, and after again few kilometers, similarly phase B, after few kilometers, you physically change the position of the conductor like this. For the C, you can see. So this is called the transposition of conductor, which is normally used almost everywhere. For industrial customers fed by 120 kV or more, voltage unbalance in network is generally maintained at less than 1% or maximum 1.5% of voltage unbalance. In distribution network, it may be between 0.5 to 2%. Now the waveform distortion. There are 5 different types of waveform distortion. There may be DC offset, there may be harmonics, there may be interharmonics, notching and noise. Those are the different 5 types of waveform distortion. Now if you see DC offset, it is the presence of DC voltage or current in AC network. DC offset is caused by the half wave rectification. You already know the half wave for single phase or 3 phase. So this may cause DC offset. Or there may be geomagnetic disturbance. So sometimes what happens on the surface of sun, there are some eruptions, big eruptions, thousands, millions of kilometers. It is big eruptions, and it generates high intensity electromagnetic waves. So sometimes you hear, okay, many satellites are out because of the eruption at sun. Okay, but now there are thousands of satellites, so other satellites, they take care of the communication system. But this happens very often. And even in Quebec, in my home province, in 1990 it happened. There was a big eruption of electromagnetic waves from the surface of sun, which reaches the earth between 24 hours to 72 hours. And that induces the current on the earth's surface on high transmission, high voltage transmission line. So it saturates the transformers and other equipment because this is a DC current which is induced. And this is what happened around 30 years ago, 35 years ago in Quebec. So all the high power networks were down for many days. So they did not know what happened, but then they analyzed it, then they came to know this was caused by those eruptions at the surface of the sun. DC component causes the following problems. May bias the transformer core so they saturate in normal operation. So basically you have to derate the transformer. So if the core is saturated, you cannot run the transformer at 100% load. You may have to derate it, otherwise it may heat up because of the additional losses and may reduce the transformer life. DC component causes even harmonics, second and fourth. It may cause problem in fifth harmonic passive filter. It may amplify fourth harmonic. Fifth harmonic filter may amplify fourth harmonic. Okay. It may cause electrolytic erosion of grounding electrodes and other connectors. Now the harmonics, you know, in US, in North America, we have 60 Hertz, here you have 50 Hertz, okay. So normally many loads are linear, but many different types of loads are non-linear in nature. Okay, so the current drawn is distorted. So if you do the Fourier transformation, you will come to know. We will see here. So if you have, suppose, this current, okay. So if you do the Fourier transformation, the fundamental component of this is the fundamental component, You can see this, I think this is 50 Hertz. And then you have the third harmonic, like in half load, in half cycle, you have 3 half cycle. Okay, so this is the third harmonic. Fifth harmonic, you have in 1 half cycle, you have 1, 2, 3, 4, 5. 5 half cycles for fifth harmonic. And for seventh, you will find the 7 half cycles. So frequency is 3 times of fundamental, or 5 times of fundamental, or 7 times of fundamental. So if you have just an example of a load, single phase diode bridge rectifier with RL load. Okay, so the currents, so here you have single phase like this. Okay, so if you see the currents here, this is the type of a square wave, and if you do the Fourier transform, you will see all types of harmonic: third, fifth, seventh, ninth, 11th harmonic. If you have a single phase diode bridge rectifier with RC load, so you can see the current is very peaky and it has a lot of harmonics. In general, even harmonics are negligible. They are perhaps most of them present because of the DC component. For 50 Hz fundamental frequency, the principal harmonics present are third 150 Hz, fifth harmonic 250 Hz, seventh harmonics 350 Hz, ninth harmonic. See, and if you have a 60 Hz, then third harmonic 160 Hz, fifth harmonic 300 Hz. So this is how you can multiply 60 by 3, 60 by 5, and you can know the frequency of the harmonic. It may cause the following problem: increase in losses in conductors and equipment, fuses, transformer, wherever the current flows. Why the losses will increase? First thing is the ohmic losses, you know. And then perhaps you might have studied skin effect. Like skin effect is what? You have, suppose this is the conductor. If frequency increases, then the current will remain near the surface. Most of the current will remain near the surface of the conductor. So this is what is called skin effect. Because of that, the resistance increases, so losses will increase. But then you have electromagnetic losses also, like hysteresis losses or eddy current losses in core of the transformer or core of the machines. So hysteresis losses, they are proportional to the frequency, and eddy current losses, they are proportional to square of frequency. Okay, so suppose you have fifth harmonic, then hysteresis losses will increase 5 times in the core. But if you have eddy current losses, then 25 times more eddy current losses. So which will heat up the transformer, and you cannot load the transformer to the full capacity. You will have to derate the transformer, otherwise it will decrease the life of the transformer because of the extra losses. Degradation and considerable reduction of capacitor's life, because capacitive reactance, you know, 1 upon omega c. So if frequency increases, then Xc will decrease and it will attract the higher frequencies current. So more higher frequency current will be attracted by your capacitor. Like I was telling you example of the neighbor's load was overloading the capacitor of another customer which did not have the non-linear load, but non-linear currents, harmonic current generated by another customer, they were attracted to other capacitor nearby, and it was overloading, heating the other customers, and it may decrease the life expectancy. Voltage distortion, it may alter the functioning of many devices, like because of the zero crossing and those things. Heating and torque pulsation in motors. Why there will be heating and torque pulsation in motors? Because of the harmonic. For example, I will draw a figure here. Suppose this is the stator and you are supplying the currents here, IA, IB, IC. Suppose this is an induction motor and then you have a rotor here, okay, conductors. So these currents, they will generate the rotating magnetic field in the air gap because of the fundamental frequency. Suppose we have 50 Hz or 60 Hz. So this is the rotating magnetic field which is generating a torque at the surface of the rotor, and rotor will start moving in this direction. Depending on the frequency, 50 Hz, here you have 50 Hz, this will be the rotating speed of the rotating magnetic field because of the fundamental components of the current. Now, suppose you have fifth harmonic here. You have fifth harmonic in B and fifth harmonic C. So, fifth harmonic current is there. Now, the fifth harmonic current will also generate rotating magnetic field, right? And that rotating magnetic field will rotate at what speed? 5 times of the speed of fundamental. Okay, so rotating magnetic field created by the fifth harmonic, and fifth harmonic is what? It's a negative sequence harmonic. It means it will rotate in the reverse direction. It will generate the magnetic field, rotating magnetic field in the reverse direction with 5 times of the speed, but 1/5 of the amplitude of the fundamental, right? So fifth harmonic will not go like this, it will go like this in the reverse. Suppose this is the direction of fundamental, F1 if we say, so this is the direction of F5 in the reverse direction, 1/5 of the amplitude but 5 times the speed. So it will have its own torque at the surface of the rotor. So the vibrations will take place. Now suppose we have the seventh harmonic. Seventh harmonic in phase B and seventh harmonic in phase C. What is the sequence of seventh harmonic? It is the positive sequence. So seventh harmonic will generate the torque in this direction, but 1/7 of the amplitude of the fundamental, but 7 times the speed of the fundamental. See, the different torques are created at the surface of the rotor because of the fundamental frequency, because of the fifth harmonic, because of the seventh harmonic, maybe there are 11th or 13th harmonic. That depends what kind of voltage was there, right? So this will cause heating and torque. This is what is the torque pulsation. And heating, why heating? Because you have a fifth harmonic, you have a seventh harmonic. So in the core of the machine, there will be ferromagnetic losses, hysteresis losses, eddy current losses. Hysteresis losses will be 5 times, or eddy current losses will be 25 times. So this will all cause the heating of the core of the machine. Telephonic interference is caused by the harmonics. Large neutral current consisting of third harmonic. So third harmonic is what? Zero sequence. zero sequence harmonic. So this is what, there are three currents coming, ABC, IA, IB and IC. So in ideal condition, the sum of three currents should be zero. But if you have the harmonics, third harmonics is zero sequence harmonic, IA 0, IB 0, IC 0, they are in the same phase. They will not cancel out. The sum of zero sequence harmonic is not zero, it is the sum. Basically, it will increase. So this is what happens, that if you have a non-linear load, different harmonics are generated, including the zero sequence harmonic, third, sixth, ninth, but not sixth, sixth is the even harmonic, maybe the ninth and 15th and so, and they will add up and finally it will go to the neutral, and that neutral current may be 2 times, 3 times of the rated current of the cable, neutral cable which you have put. So that may become heated, and if the engineer does not pay attention, it may also burn out. So sometimes in the worst case it may happen. There are so many problems caused by harmonics. Many other problems, malfunctioning of energy meters and protection relays and circuit. This is just one example. There are many standards for harmonic producing apparatus connected on electric motor. Two important standards, IEEE standard 519, which was originally introduced in 1992 and it was very popular standard, and that standard is still going on. What they have done, they have done some minor adjustment in 2014, and then 2022 also they did minor. But most of the things still remain, the harmonic limits and those things, they still remain the same. So what is the title? IEEE standard, initially it was IEEE standard recommended practices and requirements for harmonic control in electric power system. But later on in the modification, they dropped this term. So now I see IEEE standard for harmonic control in electric power system. This document provides guidelines for harmonic current and voltage distortion levels on distribution and transmission network. And there was a second standard, IEC 555-2, but it has been superseded by 61,000 this. So this is to set the harmonic emission limits for appliances and similar equipment connected to public low voltage powers network, but this is especially European countries, they follow it. But in North America, we follow IEEE standards. Then another way for distortion may be interharmonics. So what is interharmonic? See, this is, suppose we see, okay, this is the current, it is distorted and it has, see, 1, 2, 3, 4, 5, 6 and half, 6.5 half cycles. It is not 5 cycles, it is not 7 cycles, 6.5. Okay, so this voltage and currents having frequency component that are not integer multiples of the source frequency are called interharmonics. So these are interharmonics. These are caused by non-linear loads, for example, R furnace, static converters, cycloconverters. Sometimes utilities inject telecommand signals of interharmonic frequencies to control consumer relays. So this is what done by some utilities companies. Interharmonics cause the following problem. Same type of problem as caused by normal harmonics, overloading of series passive filters. So because it may not be 5, it will be 5.5 or 4.5, but it will overload your passive filter. Drop of voltage during commutation, notching. So earlier I was thinking they are still talking about notching. This was in 1992. But then I verified in IEEE Standard 519 2014 and even 2022, they are still keeping this thing because thyristors are still very much in use for higher power application. Okay, so this is what is the notching caused by commutation overlap. Commutation overlap, suppose I draw a diagram. You already know, perhaps many of you already know commutation overlap. So this is by one set of, suppose we say it is a single phase load, one set of thyristor IT1, IT3, then these currents are by IT2 and IT4. So this is the ideal condition that you are considering, that they are switched on and off instantaneously. But in actual practice, it does not happen like this. You see, there is a commutation overlap. Okay, so during that time, both sets of thyristor, they are in conduction. Okay, so this is the commutation overlap and it causes the voltage drop. During the normal functioning of converters, AC source inductance prevents the instantaneous current, because in ideal condition we say, okay, we are not considering any inductance or impedance, so we could see the straight line increase or drop of the currents. But in actual practice, that inductance prevents the instantaneous change of currents. So because of that, there is a overlap. This overlapping phenomena causes the reduction of voltage called notching. So you can see this is the depth of the notch and this is the width of the notch at say some alpha degree when we switch on the thyristor. Depth of the notch, you see, this is the load, this is the source, and this is the principal transformer, this is the reactance of the principal transformer, this is the reactance of the cable, and this is the reactance of isolation transformer. And if you see this point of observation from here, so you can see the depth of notch is equal to the reactance of the principal transformer plus the reactance of the cable plus isolation transformer. So if you have very less value of reactance of principal transformer, then you can reduce the depth of the notch. And width of the notch is given by this formula, and if you calculate the surface, so this is the depth multiplied by the width given by this equation. The limit generally admissible for the depth and surface of the notch is defined in IEEE for 600 volt distribution network, and this is the surface, this is written in special applications, general and dedicated systems. So limits are, have a special application like you are in the airport, so limits are more than 10% depth, and voltage microsecond. For general be increased to 20%, and for dedicated go for 50%, because there is no customer nearby, so it will not affect the other people. Allow those limits. By notches is about zero crossing synchronization with source voltage, because notching may cause crossing. For example, here this depth, suppose it goes like this, then it may be seen zero crossing, and your converter may try. Mitigation methods: an isolation transformer or a line reactor each drive, which will increase the value of XTI and surface of the notch. Adding a filter, this filter may solve the problem. Okay. Noise. These are the undesirable signals. We're talking about wave for distortion, because we saw that these are the undesirable signals with minimum 200 kilohertz superimposed on voltage, even on the neutral current. This is caused by power electronic devices, arc equipment, by improper grounding. The following problem: malfunction of electronic devices and programmable logic controller, mitigation solution, filter, isolation transformer, line conditioner. Now coming to the flicker, voltage fluctuation. You can see the voltage like this amplitude plus minus maybe 2. So this is called the voltage fluctuation or flicker. Flicker causes physical to the eyes because of repetitive illumination of the light. Most of them are affected by this phenomena. Flickering, you can see 5 Hz to 15 Hz variation, plus minus 2% of the voltage. In industrial load, for example, soldering machine, arc furnace, large motors with variable load may cause the voltage fluctuation. So earlier we were thinking that okay, voltage fluctuation, flicker is there, and it causes the incandescent lamp to blink like this. But finally, I found out that it affects LEDs also. Because once I brought LED lamp and I put in my house and I used a dimmer, and at certain value I saw the LED lamps, they are also fluctuating. Okay. Even voltage fluctuation instability can cause LED lights to flicker. LEDs are sensitive to voltage changes, and when the voltage supply to them fluctuate, it can disrupt their steady illumination and result in visible flickering. LED light flicker may be caused by voltage fluctuation, incompatible dimmer switch. So in my case, because in Canada we don't have voltage fluctuations, but then I realized because the dimmer I bought from somewhere else and the lamp bulb I bought somewhere else, perhaps they were not compatible at certain limit. So incompatible dimmer switch may cause it. Overloading of the circuit, too many LODs are connected to a single circuit, poorly matched power supplies and voltage instability, this may cause. Maximum sensitivity of the eye and its tolerance to flicker is between 5 and 15 Hz.